Hi, this is Mrs. Downey with Algebra 2. Today we're moving on to section 2 in chapter 6. We're going to start out by multiplying and dividing radical expressions, and then after we gain that objective, we'll move on to adding and subtracting radical expressions. And so for your bell work, I want you to begin by writing in your math journal. I want you to create and write down on one line 3 numbers with the same powers. So I will do 3 as an example. About 2 to the third, 5 to the third power, and 8 to the third power. There are my 3 numbers with the same powers. Next, skip a few lines to leave some space for you to work in. And then I want you, in the second line, line B, create 3 radicals with the same index. Okay, after you create these, leave some space. Also, now, for the first 3 numbers that you created, the 3 numbers with the same powers, I want you to try. You may not know how to do these, but I want you to try. I don't know is not an answer. So I want you to try to multiply these 3 numbers together into one number and exponent. So do that now. Just quickly give it your best shot. Right or wrong, do what you think is correct. And then for the next 3 radicals that you created, I want you to do the same. How would you multiply those 3 radicals together into one radical? And do that. Okay, if you need more time now, you may pause the video. And we're going to move on. Okay, so here's a couple of examples to the bell activity. So here's 2 numbers with the same exponent. 2 squared, 3 squared. And then when we multiply those together, we have open paren, 2 times 3, close paren, squared. Okay, so that would turn out to be 6 squared, which in the end would be 36. Okay, so when you multiply powers, if they're the same, you keep that power and you multiply the base. Okay, so you keep the power. If the powers are the same, you keep the power and multiply the base. Down here, here's another one. 4 cubed times 5 cubed. Their powers are the same, so you keep the power here and multiply the bases. 4 times 5. So this would become 20 to the third power, which would be 20 times 20 times 20. And for the same index, here's a couple of examples using 2 numbers. We have the square root of 2 times the square root of 3. Well, our indexes are the same. Because our indexes are the same, we can combine those into one index of 2, or radical 2 times 3, which would be radical 6. And here we have the cubed root of 4 times the cubed root of 5. So because these indexes are the same, because the index is the same, we can just keep the index and then as the radicand multiply the initial radicands, 4 times 5. So this becomes the cubed root of 4 times 5, or the cubed root of 20. So this brings us to a property about combining radical expressions with products. It says if the nth root of a and the nth root of b are real numbers, then the nth root of a times the nth root of b equals the nth root of a times b. So let's put this to use. Our first problem, multiplying radical expressions, asks us, can you simplify the product of the radical expressions and explain? So the first problem says cubed root of 6 times square root of 2. Well, you need to look at the index. We've got a 3, and this one would be a 2 because it's square. If there's no index there, it's assumed to be 2. So 3 and 2. They're not the same index, so you cannot multiply those together. So the answer, no, the indexes are different. The property above does not apply. The property on the previous page does not apply because the indexes are different. B, so we have cubed root of negative 4 times the cubed root of 2. So our indexes are the same. So we can do the multiplication property on the radicands. So this would become radical 3 and negative 4 times 2, which would become the cubed root of negative 8. And we know that that's going to be equal to negative 2. And we don't use absolute value symbols because this was an odd index. Okay, our got it's are here. If you'd like more practice at this point, pause the video, work these out, and then we'll continue. Okay, so moving on. If the radicand of the nth root of a has a perfect nth power among its factors, you can reduce the radical. If you reduce a radical as much as possible, the radical will be in its simplest form. For example, consider radical 24 and the cubed root of 24. So let's look at the first one. Square root of 24 is equal to, so the first thing we want to do is write this in terms of something that we can square in the factors. So we know 4 is a perfect square, and it's a factor of 24, so we'll use it. So our index is 2, so we want to try to make things power of 2 so we can clear them. So we have 4 times 6, and we can rewrite 4 as 2 squared times 6. And now that would be equal to square root of 2 squared times the square root of 6, which is equal to square root of 2 squared is 2, and we're going to leave the square root of 6. So 2 square root of 6 is in its simplest form. Okay. Next, look at the cubed root of 24. So the first thing we're going to do, we need to write things in cubes so we can clear them. So the first thing, we know that 8 is a perfect cube of 2, so it's going to be 8, which is a factor of 24, so we'll use it. 8 times 3, which is equal to the cube root of 2 cubed times 3, and then split them up. The cube root of 2 cubed times 3, cubed root of 3, and we can clear that out. Simplify the cubed root of 2 cubed is 2, and leave the 3 cubed root of 3, and that's our answer. This is Miss Downey continuing with the second part of Chapter 6, Section 2. We're now on Problem 2. So now we want to simplify a radical expression. It says, what is the simplest form of the cube root of 54x to the 5th power? So again, we're going to apply these concepts we just learned. And the first thing we want to do is find all the perfect cube factors. So we have 3 cubed, which would be 27. Oops. So 3 cubed, 3 times 3 times 3 is 27. And then times 2. So 27 times 2 is 54. So we found a cube factor of 54 being 3 cubed. Now we want to split our x fifth up to an x with a cubed. So there's our x cubed, and that leaves us with the x squared. So now that we've found all of our perfect cube factors, now let's regroup, and that we want to group our cubes together. So here's our cubes, the 3 cubed and the x cubed, and then the leftovers, the 2x squared there, using our new property. And then we want to clear this out now, simplify that to 3x, and then we're left with the cube root of 2x squared. So that is our final answer, 3x times the cubed root of 2x squared. I like to think of this as when you have this index and then your powers match the index, they sort of cancel each other out. And when you can clear all those, you take away your radical sign, and that just leaves you with the 3x. It says, how do you know when you're done simplifying? Well, you're done when the radicand contains no perfect cube factors, or whatever your index is. In this case, it was cube. Here's our got it for more practice. And pause the video if you'd like to work it. So in problem 2, it involves simplifying a cube root. So the absolute value symbols were not needed because it was cube, it was odd. We only put them on the even. So remember to combine the nth power of a, nth root of a and the nth root of b by multiplication. And both radical expressions must be real numbers. So let's look at problem 3. Simplifying a product, we're still multiplying. What is the simplest form of the square root of 72 x cubed y squared times the square root of 10 xy cubed? So we've got our think and write here. So you need to multiply the radicands to find the perfect square factors. So you think about what you have here. Because they're both squares, we can combine them. He's a square root, he's a square root, so we can combine it into one statement here. And now you want to do the math. So you have the 72 times 10, which is 720, and the x cubed times x, well, you just add the powers, right, because it's like x to the 1. X to the 3 times x to the 1 is x to the 4th. And then y2 times y3, you keep the base and add the powers. So it becomes y to the 5th. So now that we've combined these, now we've got to pull it apart with a perfect square factor of 720. And we know that 144 is a factor of 720. And 12 squared is 144. So we can rewrite 720 as a product of 12 squared times 5. And then we want to take the squares out of our x's and y's. So we have x squared squared and y squared squared times y. So now we want to put all of our squares together. So we've got our 12 squared, x squared squared, and our y squared squared. And we're just left with our 5y. So the 5y goes over here, and all the squares come over here. Now that we have all of these squared, we can remove the squares and clear the radical. And it leaves us with our radicand. 12 times the absolute value of x squared y squared. And because they are squared, that's an even, so it's going to have the absolute value, times the square root of 5y. Now, because these are squares, there's no way we will ever have a negative sign in these. They're even powers. So we can take the absolute value signs off, and it leaves us with 12 x squared y squared times the square root of 5y. So that is our simplest form. Here's our got it for problem 3. If you'd like more practice, pause, work the problem, and come back. Okay, so now we're back, and we're going to work on multiplying, which we did in the beginning, and dividing. So now we're going to work with division of radicals. So since we define division in terms of multiplication, we can extend this property for multiplying radical expressions. So on the left is the multiplying that we discussed earlier, and on the right is our dividing. And now, if the indexes are the same, we can write a quotient of roots as a root of a quotient. So here we have the radical 2 over radical 3. We can rewrite that as 1 radical, or square root of 2 over 3. And here, likewise, we've got the cubed root of 4 over, or divided by, the cubed root of 5. And we can rewrite that as 1 cube root of 4 over 5. And that's all that is. So here's the property of combining. You may pause and write this if needed. Now let's look at problem 4. It says dividing radical expressions. What is the simplest form of the quotient? So it says, let's first think about our answer. Will it have absolute value symbols? Well, we've got odd powers here in our radicand, but they're square roots. So, what do you think? Both the divisor and the dividend already require that x be non-negative. So let's think about why that is. Okay, continuing with problem 4, we're dividing radical expressions. What is the simplest form of this quotient? And for the first problem that we have, it is the square root of 18x to the 5th divided by the square root of 2x cubed. So the first thing we want to do is combine this under one big radical sign. So we have 18x to the 5th over 2x cubed, and we can separate this if you'd like. And we know that's going to be 18 over 2 times x to the 5th over x cubed. 18 divided by 2 is 9. and that becomes x to the 5 minus 3, which is x squared. So now we can rewrite that as square root of 3 squared times x squared. So now that they're all squared, we can cancel that out, and it becomes equal to 3x, and that's our answer. Our next problem, we have the cubed root of 162 y to the 5th over the cubed root of 3y squared. So the first thing we want to do again is combine it under one radical sign and then process them. So 162 divided by 3 is 54, and y to the 5th over y squared is y to the 5 minus 2, which is y cubed. So now that puts us here. Now we want to write things in a cube factors if we can. So we know 54 has a cubed root factor, which is 27. And 27 is 3 cubed. So we're going to use that. So it's 54 is 27 times 2. So there it is, 27 times 2. And they've just left out this step here, if you're wondering how they got from there to there. So they left out this 27 times 2 times y cubed. All right. So now they just split it up, 27 y cubed in the first radical, and then the cubed root there. Okay, so now we can rewrite this as 3 cubed y cubed. So the cubic root of 3 cubed y cubed, and then this is just a straight copy down, cube root of 2. So now this becomes 3y and times the cube root of 2. So that's our answer, 3y times the cubed root of 2. Here's our got it. So you can pause if you want extra practice. So another way to simplify a radical expression is to rationalize the denominator. Remember when we used to clear square roots out of the denominator? We're still going to do that, but with more than squares. So we've got to make that denominator something we can work with. So we rewrite expression so that there's no radicals in any denominator and no denominator in any radical. Okay, so that's the rule. So when we have a radical in the denominator here, we've got to clear it. So remember back in Algebra 1, what do? We would multiply it by 1, but we would make 1 fit our needs. We need to clear that radical, so we'll make 1 square root of 2 over square root of 2. So we haven't changed this fraction, we've just changed the way it looks, but to fit our needs, because we want to clear that radical. So when we multiply that denominator, radical 2, or square root of 2 times square root of 2, we just get 2. So now we've multiplied this fraction by 1, and our 1 is square root of 2 over square root of 2, and we cleared the denominator to get 2. So it's a straight multiply on this, so 1 times the square root of 2 is square root of 2, and on the bottom, square root of 2 times square root of 2 is just 2. So this is called rationalizing the denominator. We cleared it to a real number. So we're going to use that in our last problem of the day, rationalizing the denominator. What is the simplest form of the cubed root of 5x squared over, or divided by, 12y squared z? So the first thing we want to do is split it up. And so before we were putting it all together. Now we have to split it up so we can work with it independently. So we're going to take it from this, the cubed root of that whole fraction, and then we're just going to put the cube root over the denominator, or numerator, and the denominator. Okay, now we've got to clear this crazy denominator there. All right, so how do we choose what to multiply it by? So we need to choose a cube root with a radicand that will make each factor of the radicand in the denominator a perfect cube. So we've got to try to make everything there a perfect cube so we can clear the denominator. So what do we need? So the radicand in the denominator, we need a 2, 3 squared, y, and a z squared to make these factors here perfect cubes. Because see, if we multiply the 2 squared by one more 2, we'll have 2 cubed. If we multiply this 3 by 3 squared, we'll have 3 cubed. If we multiply y squared times y, then we have y cubed. And if we multiply the z times z squared, we'll have z cubed. So that's what we're going to use to get our denominator and to rationalize our denominator. So we're going to multiply by the cubed root of these things to turn everything in that denominator to a cube. And if we do it to the denominator, we have to do it to the numerator, because what are we doing here? We're just multiplying this by 1. Okay? So when we do this, it cubes everything on the bottom, and then you just combine and do the math on the top. So we have 3 squared, which is 36 times 2 times 5 over here. That gives us 90. And then we have an x squared, y, z squared. And there that all is. So you just do the straight multiplication. And then on the bottom, notice now everything is cubed. 2 cubed, 3 cubed, y cubed, z cubed. That was our goal from the very beginning, because we have to clear this out because our index was 3. If our index had been 5 for all this, we would have made everything a 5th power. But because we're trying to clear the cube in our index, we make everything a 3, power of 3. So now that we did that, now we can finally get rid of that radical sign in our cube roots. And we end up with 2, 3yz. 2 times 3yz. Okay, and then the top is going to stay the same, the numerator. And that 2 times 3yz becomes 6yz, and we are done. That's as far as we can take it. We can't do any more math between the numerator and denominator because they're not like radicals anymore. Okay, the denominator is not even a radical, just the top. So you can't do any more math or simplifying there. It's in its simplest form. So our got it is here. So again, pause and work on this. And that completes our assignment today. And I've asked all the students to work on the workbook 6.2, practice K, and we're going to work problems. Okay, so we're working problems 2, 3, 4, 5, 7, 8, 10, 11, 15, 16, 19, and 20. Okay, and work on this for the rest of the hour, and it is due tomorrow morning. Thanks for watching, and work hard.